Hello everyone. As they presented me, I'm Salvador Medina, PhD student at the Language Technologies Institute in Carnegie Mellon. And I worked in collaboration with Sarah Taylor from the University of East Anglia, Mark Tiede from Haskins Labs. He helped us capture the data. My advisor, Alex Hauptmann, who has supported me for the last 5 years of the PhD, and Iain Matthews from Epic Games, who's also an adjunct faculty at CMU and has invited me into his crazy projects. So, as we know, in the last decades, the tongue motion has been studied widely towards language generation and language pathologies. And as time passes by, technology also advances, making it better to get a better understanding on how the tongue moves. For instance, as Vincenzo told us before, Xray has been used, where you can actually see the pose and the motion with some caveats. One of them would be a low frame rate, even though the technology has kept on advancing. However, this is not healthy at all. You cannot put a subject on for long periods of time exposed into the radiation. Therefore, you cannot generate a large-scale data set based on this. Other two methods are MRI scans and 3D ultrasound. Lately, MRI scans have increased their sampling rate. They went from 25 frames per second all the way up to 88 frames per second. But again, there's a caveat. They've got really low resolution images, and it requires some post-processing to track the tongue motion. Or in the case of ultrasound, you cannot capture completely the tongue tip because it's being shadowed by the jaw or the air that you can find under the tongue. Also, we have electromagnetic articulography, or EMA, where you actually have high sampling rates and precision. You can capture up to 1 kilohertz, so more than 1,000 samples per second, and the error is sub-millimeter. However, that doesn't come for free. You have a sparse representation where the number of sensors that you can actually use to capture the tongue is limited by 2 factors. One is that the sensors must be separated by a certain distance such that the readings do not interfere with each other. And the other one is how much that apparatus can actually handle at the same time. And generally, what they do when they're capturing EMA, they do it mid-sagittally, so you only have one line, the midline of the tongue. Here, I can show you, we have the upper lip over here. That's what you're looking at. Here's the lower lip. This is the lower incisor. This is the tongue tip. You have the tongue body or blade and the tongue dorsum. So the tongue is only represented by a single line. And this is how it would look like.
Orange juice tastes funny after
when you visualize this data.
Orange juice tastes funny after toothpaste.
So what we did for this work was add some parasagittal sensors or lateral sensors. And what you see here is the sensors that we added were 2 on the tongue, on the left and the right-hand side of the tongue blade or the tongue body, then 1 on the right lip corner, and 1 more on the jaw. Which is located between the canine and the first premolar. Based on this, you can get a better idea in 3D, actually, of what's happening.
Orange juice tastes funny after toothpaste.
Even though it doesn't have the resolution, as Vincenzo showed us, you get a better understanding in 3D of what's happening there. So the main contributions of this work are: we are providing a new large-scale multimodal speech-to-EMA tongue motion dataset with additional parasagittal sensors to the midsagittal sensors. And we made an analysis to just check that the actual parasagittal sensors are providing relevant information that you could also be capturing on the midsagittal setup. For the data capture, we use the Carstens AG501. If you've been walking around, you've seen the apparatus out there in the hallway, and we captured the data at 250 hertz. The sensor position, we built a biplane as the reference plane. The biplane was set up by putting 1 sensor in the upper incisor and 2 on the mastoids. We only captured the data from 1 subject, an British English male. and recorded almost 1,900 clean samples, from which 720 samples are from the Harvard set, where the actor or subject uttered it twice, once at a regular pace and the other one at a fast pace. We believe that will be useful for the research community to see how the changes in articulation depending on the speed on which the subject speaks. And the rest of the samples are just sentences from this TIMIT data set. The total duration of these data sets is almost 2.5 hours of synchronized audio and EMA landmarks. So to check the quality of the data that we have, we made a diphonic analysis. We took advantage of our experimental setup where we already knew the transcripts of the audio. So we used the Montreal force aligner to extract the phonemes from the whole audio, and then just calculated the diphones in an n-gram, sequential n-gram approach, where we got a little bit above 1,150 diphones, and selected only the diphones that had the structure of vowel, consonant, consonant, vowel, and had more than 86 samples. This filter resulted in a total of 142 unique diphones that cover around 60% of our data. So our data is even richer than that. And then we proceed into a data analysis that it's just correlation analysis of the motion of the parasagittal sensors with respect to the midsagittal sensors. And we also made hello analysis on the width and curvature of the tongue, just to check how good the data was. So for the midsagittal comparison with the parasagittal motion, we just use Pearson's correlation coefficient, R. And this is our reference frame, as you can see there. The antero-posterior direction is being described by the x-axis. The mediolateral or direction is being described by the y-axis, and the vertical direction is described by the z-axis. Then what you see on the plot on the right over here, you will see in blue, it's the tongue blades in shades of blue. Then on red, it's the tongue dorsum. And on greens, you will see the tongue tip. Then the shades, the darker they are, it refers to the x direction or back to front. And we can see that most of them are located on the right. So there is a huge correlation of the parasagittal sensors with the midsagittal sensors, because whenever the tongue moves back and forth, everything moves back and forth, right? So no surprise there. But what we really liked on the results over here is that if you look at this light shade of colors, especially on the tongue dorsum and tongue blade, they have zero correlation. This line over here, it's a zero correlation, and on this side, it's a negative correlation. So actually, there was something going on there on the mediolateral direction for some diphones. Looking at the top of the chart, I couldn't fit it in the full slide. We found that the diphones that end in alveolar consonants as z, s, and n, they had a really low correlation and even negative correlation there, again, of these two lateral sensors on the tongue with respect to the tongue blade and tongue dorsum. However, for the alveolar T, that didn't happen. Most of the light ones are over here. Then moving into the width and curvature analysis, we used as a width proxy the L2 distance between both parasagittal sensors on the tongue. And as a proxy of the curvature of the tongue, we use the Menger curvature. As a brief reminder, the Menger curvature is just the inverse of the radius of the circumference that you can fit through 3 points. In this case, the 3 points are just the projection of the lateral blades sensors along with the tongue blade into the coronal plane. The coronal plane is what you're looking at over there. And given the sequence in which we fed and we actually computed this, when you've got a positive value in the curvature, that means that you've got a downward curl as the one that you're looking at right there. And then you have a negative, whenever you have a negative curvature, it means that you've got an upward curl on the tongue. Over here, what you see is in orange, you see the curvature. So we sorted out this correlation plot or this plot on, based on the curvature. And in blue, what you're looking at is the width. The width goes, the distance between the sensors goes between 21 millimeters up to 25 millimeters. And as we can see, we see a slight negative correlation between the curvature and the width. In particular, if you look at the bottom, we can see a cluster of diphones like over here, down here, where the diphones that begin with an R and it's followed by a vowel, you've got a wide tongue, which is represented by this, with an upward curve, which is represented by this negative curvature. Also, one of the main issues of analyzing the data in that way is that you're losing the total dynamics, which is the main point of the EMMA capture. So for this, we visualized every single diphone, and what you're looking at here is the dynamics is being encoded in it's color encoded over there, following the rainbow color map. If we remember from elementary school, we go from indigo all the way to red, passing through some blues, then yellow, orange, and red. So in this case, I'm showing the diphone, like all the samples that we captured for saw, which we have here, saw. And we can see that the tongue tip, it's close to the palate over here. And the lateral, the parasagittal sensors are also close to the palate at the beginning. And then, as we go into the open vowel, everything goes down and then goes into a resting position over here, which ends on the red. We will be providing this for all the diphones on the website. I invite you to read the paper. The website link is there. And as a summary, what I'm presenting here is that we are providing a new large-scale multimodal tongue motion dataset. It has synchronized audio, lips, jaw, and tongue landmark positions coming from EMMA. It is only from one speaker, a British English male. It's approximately 2.5 hours of phonetically balanced samples, which contains midsagittal and parasagittal tongue sensor motion. We made a diphonic analysis to check the quality of our dataset, and we found that there is a low correlation in the mediolateral direction between the parasagittal and midsagittal sensors, and the width and curvature of the tongue enable a characterization of the diphones. Finally, we provide some visualization of the diphones, and the code will be available for you to actually visualize it. And that would be it. Thank you very much.
Are there any questions in the room? Does not? Yes. Yeah.
So thank you for your very interesting talk. My question is very basic. In the video you showed about of the data collection, there were some dots in the face of the actor. I wanted to know what that means.
That's for future work. That's actually something that I am currently working on. We will try to provide a full data set. I'm not sure that if you also saw the image. He's got an ultrasound scanner on the bottom. So we will try to provide something that is global, that it englobes actually the facial capture through those optical markers. Okay. That's something that I'm currently working on, and I have to finish soon. And then the next step is to actually get this depth estimation from the ultrasound and provide a richer data set to the community.
Nice. Okay, yes. Thank you.
Thank you.
So we have an online question as well. Thank you for the talk. 2 hours and 33 minutes is a long time for EMMA. I would expect the census to fall off after around 30 minutes. Yes. Was this measured over multiple sessions, and if so, how did you ensure the census positions were identical?
Yes, that's a really good question. So my lead, Iain Matthews, was the one that captured, and he said that he was there for an 8 to 9 hour session. And it's true. So they came up, but what they did, they put some markers. So they marked the tongue such that whenever it would actually come up, they would put it again in the same position. So there might be a slight error, but it should be under the millimeter error of the reposition. Thank you.
Okay, thank you. Any other questions from the audience? Maybe there are no online questions. If not, I think we have the time. But I will ask a question myself.
Yes.
You mentioned that you looked at vowel consonant plus consonant vowel
Yes.
diphone. So were there no words with like clusters or three consonants in the words medial consonants, or did you just skip the middle consonants?
Yes,
or just at the side?
Yeah, that's a pretty good question. Actually, on the first version of the paper, we inputted every single diphone, but then the reviewers told us, "Hey, could you please narrow that down? I cannot read the actual the actual chart that you were displaying there." So we thought that going from vowel into consonant and consonant into vowel would provide the richer information, right? Because you have a change from a static point on the consonant and then with some dynamics onto the vowel. I mean, by all means, I will provide every single diphone that we have. The data is there. I process that, and I hope that the research community makes use of it.
Thank you. And another question at the back.
Thank you. You're one of the first to do parasagittal sensors at the side of the
No.
Oh, that was not my question.
Oh, okay.
Did you see any asymmetry between these two sensors?
Yes, there is. Actually, if you look at the video, there's a certain asymmetry where the right sensor is a little bit slight forward with respect to the other one.
And not in position, but in movement.
Oh, the movement? Yes, of course. Actually, whenever we visualize the diphones, you can see that sometimes that needs to go into further analysis, but you can see that one of them, especially for this subject, he tends to move the tongue on the right-hand side a little bit more upwards, especially when pronouncing open vowels. That's where I see that movement.
Yeah, because I've seen a talk by someone doing bladography, the contacts, and they saw all kinds of asymmetries.
Yes,
contact.
totally. And that's something that we should be aware of, that we are not symmetrical, right?
Yeah,
we humans are not perfect. We're not symmetrical. So asymmetries are definitely in there, and that would be super interesting to actually analyze.
Actually, we know nothing about that.
Exactly. Exactly. Thank you.
Wait, and there's two questions. I don't know who was first.
Thanks, Jean. I was just closer. I was just wondering, maybe I missed that in your talk. How did you time segment those diphones? Did you segment them based on the acoustic signal, or did you base on some sort of articulatory onset of those?
It was based on the acoustic signal. Again, I used the Montreal forced aligner.
Right.
So what it does, I think it analyzes the formants, and that's how it actually segments the...
Right, but of course, the articulatory sort of segment might start quite a while before the acoustic segment.
Yes,
so the movement towards the S starts before that, and then...
Yeah, that's something that I would need to dive deep further into how that's segmented.
Yeah, looking forward to that. Thanks a lot.
Thank you.
So my colleague Pierre Badin has studied quite well this 3D aspects of a vocal tract, and so I think it demonstrated that basically the midsagittal section is sufficient to determine what is happening in 3D. So my question is about since you do linear correlation, you get this problem of contact. So, you know, when you explore the side of the tongue, it's mainly in contact with the palate. So
yes.
So it's perhaps due this absence of correlation, or this low correlation is perhaps the fact that 50% of the time they are not moving.
Yes. Actually, one thing that I forgot to mention is that we made a reconstruction of the palate. For that, we took a swab with a sensor, made some traces, and then worked with some software that actually reconstructed the surface. And you are completely right. Whenever it goes into the palate, it just actually goes into the surface and tends to go sideways. That is true, especially with the consonants that have to touch with the alveolar. Yes. Yeah. Yes. This was more like a wavy hello and say, yeah, how much information are we gaining from it? Thank you.
Okay, so thank you very much for the talk.
Thank you.